You can read a variable from outside a function, but the moment you try to change it, Python stops your code with an error. To understand why, we need to see what really happens when a function is called, the objects that live in memory, the fresh environment every call creates, and the rules of scope. Once you've written a function, it becomes a black box. That splits two roles: the programmer who writes the function as a modular reusable piece of code, and the user who simply calls it. The user just invokes it, the way we called bisection root earlier, to build something more complex without knowing how it works inside. That's the whole point of a black box. Once you have its specification, its docstring, you don't need to know the implementation to use it. Here's a key idea. A function definition simply creates an object inside memory, a function object, and its name is the name of the function. Take our function SumOdd, which adds up the odd numbers between two endpoints. Defining it drops an object into memory holding some code named SumOdd. This mirrors an ordinary variable. When we write low is set to 2, we create an object, the integer 2, named low. Defining the black box is the same move. It creates a function object named SumOdd. So memory might hold three objects side by side, SumOdd, low, and high. Only a function call runs the code. Defining the function never runs it. The object just sits in memory. When you call SumOdd, you pass in arguments, here low and high, holding 2 and 7. The call matches them to the function's parameters in order. The first parameter takes low's value, the second takes high's value. The function does its work and returns something, either a real value or none. That returned value replaces the entire call. So when we write my sum is set to SumOdd of low and high, my sum becomes whatever the function handed back. So what actually happens during a call? Picture the main program taking a pause. It hits a function call, and that call behaves like a little mini program that must run and finish, returning a value before the main program can pick up where it left off. That mini program builds its own little environment to live in. Inside that environment, it can make variables, change them, print things, do all the work in its body. When it's done, it has a result, and it hands that result back to the main program. The crucial rule: every function call creates a brand new environment, completely separate from the main programs. The instant the call finishes, that environment disappears, and every variable born inside it disappears too. When your program first starts, it runs in what we call the global environment, the main program itself. Each call spins up a fresh environment on top. These environments barely touch, they communicate only by passing parameters in and returning values out. Because of that, two different environments can each hold a variable with the same name, and they never collide. Here's a simple function, f. It takes one parameter, x, adds 1 to it, prints the result, and returns the new value of x. The x in the definition is a formal parameter. When we write the function, no value is attached to it yet. It's just an abstract name used in the body. Now the main program, x is set to 3, then z is set to f of x. The same letter x appears, but the x inside the main program is a different variable from the function's formal parameter x. The main program's value, 3, gets mapped onto the formal parameter, and the outer name doesn't matter. Writing y is set to 3 and calling f of y will behave identically, because what we pass is the value 3. Let's trace it. After the definition, there's one environment, the main program, holding just f, a function object, not yet running. Then x is set to 3, adding a variable x with value 3 to the main program. Now the call f of x. Python creates a new environment and puts the main program on hold. This new environment is the scope of f. Its first job: find f's one parameter named x and bind the formal parameter to the value passed in. So f's x becomes 3. Now the body runs. X is set to x plus 1 takes f's s, which is 3, adds 1 and makes it 4. There's no collision because the scope has its own x. The main program's x is untouched, still on hold. The print outputs f of x4, then return x hence back 4. The moment f returns, its environment vanishes. The x inside f is gone. Back in the main program, the return value replaces the call, so z becomes 4. The main program's own x is still 3. No confusion. Now some scope nuances that aren't true in every language. First example, the main program sets x to 5, then calls f. The call makes a new scope and the main program goes on hold. We map f's parameter y to the value passed in, 5. Then the body, x is set to 1, creates a brand new x, value 1, inside f's own scope. Adding 1 makes it 2, print shows 2. The function ends, returning none, and its scope vanishes. Back in the main program, print x shows the global x, still 5. So the output is 2, then 5. The local x never touched the global 1. Middle example, again x is 5, and the calling g makes a new scope with y mapped to 5. Now the body runs print x. Is there an x inside g's scope? No. So Python does something important. When your environment has no variable by that name, it looks outward to the environment that called you, the main program called g, and it has x equal to 5. So Python borrows that value. If the outer environment lacked it too, Python will keep searching further out until nothing is left to search. So g prints 5, then prints x plus 1, which is 6. It returns none, its scope disappears, and back in the main program, print x still shows 5. Notice g read x and computed x plus 1, but never modified x. There was no assignment to x, just a read. Third example, and it ends in an error. Calling h makes a new scope, with y mapped to 5. Then comes x is set to x plus 1. This crashes. Python raises an unbound local error saying it cannot access local variable x because that variable has no value it can use. Crucially, Python does not borrow x from the outer scope the way the middle example did. Here's why. Because you assign to x somewhere inside h, Python decides x is a local variable of h for the whole function. So when it evaluates x plus 1, it looks for local x, but no earlier line ever gave h's own x a value, so the reference fails. The exact wording varies by Python version, but it's always the same unbound local error. So here's the lesson. You can read a variable from an outer scope. Python searches outward to find it, but you cannot change a variable outside your own scope just by assigning to it. The moment you assign to a name anywhere in a function, Python treats that name as local for the whole function, and reading it before you've set it fails. The middle example only read a variable and added 1 for printing. It never assigned, so it worked. And this isn't special to the name x. Writing z is set to z plus 1 inside h would fail exactly the same way. Z would be local, used before it was ever assigned. What if you genuinely want a function to change a variable in the global scope? Python makes you say so explicitly with the keyword global. Add the line global else at the top of h, and now s refers to the main program's x, not a new local one. Run it. X is 5, h adds 1 and prints 6. And back in the main program, print s now shows 6 as well. The global variable really changed. Without that keyword, assignment always makes a local. Global is how you opt in to touching the outer variable. Step back, and the model is simple. Defining a function just binds a name to a function object sitting in memory, nothing runs. Every call pauses the caller, opens a fresh environment, maps your arguments onto the parameters, does its work, returns a value, and then vanishes, taking all its local variables with it. Inside that environment, you can look outward to read variables you don't own, but the instant you assign to a name, it becomes yours, local and separate. That single rule, assignment makes it local, is what turns a stray x plus 1 into an unbound local error. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.